Okay, let's get started for the last session of this module. But before we start, otherwise I will forget. Your certificates are here, so for those that need certificates, please come and help yourself later on. And also, please don't forget to fill out the survey. The link is here, so to provide feedback about this session, the workshop in general. So the program for the rest of the morning is to learn a little bit about interactive visualizations in R. And so to start with, we're going to reuse one of the data sets that we have already seen, which is the CRC data set. So you can either load that CSV file into R, again, really read _CSV, either online with that URL there, or if you have downloaded the data locally, CRC and score train. That is, in my case, is in my data subdirectory. So I'm going to load this. And so we're going, first of all, we're going to start by creating visualizations using ggplot, as we have seen before. And then we are going to be able to reuse these figures that we produce with ggplot and kind of make them add some interactivity using another package called plotly. So here's an example. Assuming we have this CRCDF table readily available, we can produce this scatter plot using ggplot2, where we want to visualize the expression from one gene, or compare the expression of one gene against the other one. And here we will, each point will represent a patient, and we are going to color code these patients based on the group they belong to. So this is plain ggplot, as we have seen already a couple of times this week and also last week for those that were there. And so what we would like to do is to take this plot exactly as it is and add some interactivity to it. And this is something that we can do with the package plotly here. And we can use the ggplotly function and pass to that our plot p. And ggplotly understands the structure of these, this variable p, and is going to re-render it, adding to it some interactivity. So we can now hover over each of these points, and we get the actual values, expression values for the two genes, and here the groups. And by default, all these visualizations support typical actions like zooming and panning like this. And so very little effort, as long as we have our visualizations are produced with ggplot2, very little effort, and we can convert these into interactive visualizations. Just to show another example, here I take a subset of my CRC data frame, I gather it, and I produce the following line plot. this. Waiting for the figure to appear. Okay, so here's my plain ggplot figure. And I simply pass this variable to ggplotly to, again, re-render this with some interactivity. So really very little effort for very respectable output. And now this is somehow arbitrary data, but this also worked for domain-specific data. So let me reload the MSN-based package from yesterday. Load iTrack 4-plex test data. Which is an object of class NX. Displayed here. Small object with 55 spectra. Yesterday we have seen that we can extract spectra with double square bracket operator. Here, for example, the first spectrum of level 2. And we can use the plot method to create a ggplot2 visualization. Here, if we store this figure in a variable, for example, ms, we can reuse plotly to render it interactively. So here it is. And we can, for example, here zoom in into our reporter ions. We can move along the axis, and for example, here we could even move further down and see this profile mode data. Again, relatively useful visualization with very little effort, as long as we have the right infrastructure to produce our ggplot2 objects. There is plenty more to do with ggplotly, and there is a very nice documentation. There is a link to this in the lecture notes. Here at the very end, so here's an example again. And these interactive graphics can also be rendered inside interactive documents like this one. So the lecture notes here are markdown files that are rendered online, and these interactive plotly figures can be embedded into HTML documents. And so here is a book or book down documentation that provides much more information about plotly for R. But now we're going to move to another infrastructure available to our users and our developers to develop interactive visualizations. And while plotly is really meant for some transient visualizations, you have already a figure and you want to quickly visualize it interactively, add some interactivity. Sometimes you might want to develop applications with the goal of reusing them and maybe sharing them. And if you don't know how to write code, develop code in JavaScript, there is an R package called Shiny that will allow you to kind of serve and view these data from R through web applications. And so before developing our own Shiny applications, Sarah is here, and then after myself will demonstrate two examples of how we have used Shiny as part of our research and development.
So this is a Shiny interface that we created as an extension to MSStats, which is called MSStats QC. So it's under the QC tab of the MSStats.org. And if you go all the way down here, there is a link for MSStats Shiny app. MSStats QC is an open source software that provides longitudinal system suitability monitoring tools, or in other words, control charts for proteomics experiments. It allows users to import their data set here in this tab, data import and selection. And I have provided an example that users can run that for an example of the data set that they can use. And the reason we developed this Shiny application is that in laboratories, the experiments run for a very long time and may have many replicates, and it's very important for us to make sure that the measurement system for the experiment continues to perform as intended. And the reason that the system may fail to perform well continuously is due to many reasons, like technological conditions such as different laboratories, the person who's doing the experiment, or temperature of the room. So as the experiment goes on, it may goes off the limits that we expect. And it's important to detect that. And this is the reason that we developed this software, to detect those deviations from the expectations that we have for our experiments. So once we have uploaded our data correctly, we can go ahead and select some options for our data set. Like, for example, the metrics that we want to use for our analysis. Here we have 4 default metrics, but the users can have more metrics, and the system will figure that out. And if you have more metrics will appear here, in which you can select whatever number of metrics you want. So here I just select 4 metrics. And then we can select the mean and standard deviation for each of our metrics, or let the guide set decide the mean and standard deviation, in which I chose the second one. And then finally you can choose the peptides which you want to do analysis on, and in this case I select all the peptides to see the analysis for all the peptides in my data set. And then in order to decide whether the system performance is unacceptable or it's poor or acceptable, we will create some decision rules for ourselves. So here we can select that, all right, if more than 70% of our peptides are out of control, and if 2 metrics out of whatever number of metrics we have are out of control, then we will consider the system performance to be unacceptable. And then if, for example, here is the middle stage. So we will say that, all right, if more than 50% of the peptides are out of control, and if more than 1 metric out of whatever number of metrics we have is out of control, we will say that the system performance is poor. And here is the other cases where the system performance is acceptable. And once we select everything, we can go ahead and see some analysis of our data set. So here, for example, we can see some box plots where they are interactive, and as Lawrence shows, we can just hover around, or we can like zoom in to a specific part of the box plot to see like more details for like this specific type. And we have box plot for the rest of the metrics as well. And here we have other plots to show, which this one is a decision map, which is a heat map that shows where the system, or each specific metric where the system was in control, when the performance was poor, or when it was out of control, which is shown in red here, as well as some plot summaries for our metrics, where you can see river plots or radar plots for each of our metrics individually and for our peptides, whereas they are more flat, it shows that the system is not performing well. And then finally we have control charts where we can see the results of analysis here. Here is for mean, and here is for the variability of the data set. And then when the system performance is not well, the dots are appeared as red, which are like out of the expected boundary like for the data. And as you see, they are all interactive. You can hover around, see the exact value for the x-axis, and then again you can zoom in to a specific part of the data to see more detailed information. Yeah, that's it. If you have any questions, I'll be happy to answer.
And I would like to show you a second utilization of Shiny. And that is this case dedicated to the exploration of spatial proteomics, which is a big topic in my research. And so I'm going to load some data that we have already seen previously. It is. That's the hyperloggy data that we have already played with in terms of we have built, we have seen PCA plots, we have used it for higher data clustering, and the PCA plots that we have seen is this one that can be generated statically with the plot2D function that is aware of where to find the information in this object. So in this case, PC1, we have close to 50% of the variability, close to 25 PC2. So even though this is 20-dimensional data, summarizing it along 2 dimensions is meaningful. And so what we have seen here, what we have here is on this scatter plot, each point presents one protein. Gray dots correspond to proteins of unknown subcellular localization, and the colored dots represent proteins for which we are very, very certain of where they reside inside the cell. So for example, all the pink ones here are mitochondrial proteins. Here we have the nucleus, the 40S and 60S ribosomal proteins, cytosol, proteasome, and here all the ER, Golgi. So this is how the data would be visualized or statically. And so it's possible, let me check if the packages are not installed. I'm not going to install it now. But it would be possible to fire up an interactive visualization of these data here if I have my data locally and if I have the set of packages installed. But it's also possible to kind of externalize or upload these applications on the server and to use to demonstrate here. And so application that we are going to see here that works on a server run by our studio on the cloud is exactly the same. Functionality is exactly the same that we could fire up here using a function from the package. So here it is. We have 3 tabs here at the very top. One that provides general description, and in this case it's simply the abstract of the paper. We have a tab with the PCA visualization, which is exactly the same that we had dynamically. And we have a tab with the profile, so I think we have about 5,000 proteins, 5,000 dots on the PCA plot. And here we have 5,000 lines along the 20 original dimensions of the data. And so each of these subcellular localizations, subcellular regions are color-coded here, and they also, there is a legend there on the right. And we have the different labels here, and if we're not interested in all these localizations, we can remove some of these. And depending on those that are selected here, they will appear on the PCA plot, and they will also appear, or not, here on the line plot. So we have linked these different data sets. We have linked the line plot here, or the lines on the line plot, to the dots here on the PCA plot, and to the labels of the subcellular locations here on the right. What we also have here is a table that takes all the proteins and their annotation. So actually, this table here is taken automatically from the feature data of the Zen set. So these are the annotations for each of the lines that we saw on the line plot. And we can, for specific keywords of interest here, and these will then be selected here on the table. And what we can also and then select specific proteins here in the table, and whenever we select one protein, it gets highlighted on the PCA plot. And whenever there is something that is highlighted on the PCA plot, that specific protein profile is also highlighted on the line plot. So selection can be done through the table, but we can also select proteins, for example, this one by double-clicking on it. I'm not sure what my second one highlights it. Okay. But we can select specific proteins, they get highlighted here. They will also be highlighted on the table, but the table here is really long, so there is no guarantee that the one we choose here will be displayed. We could display more entries here, but everything that we select here on the PCA plot is then also automatically highlighted on the line plot here. The last bit of functionality, although this one doesn't use plotly because we already developed the application some time ago, but it also, and so it does not use plotly, but we can also zoom here and select, and so zoom inside specific areas of the plot, zoom in and zoom out. So the idea now is to develop a Shiny app altogether to get you a feeling of how to do that. It's not dramatically difficult. There are a few new concepts and somehow weird syntax or weird behavior from an art perspective to get used to. It's not particularly difficult, but certainly there is a certain overhead. So before starting and develop an application, either a simple one or even slightly more involved one, I think it requires some thinking because there ideally should be a desire to share that application with other people. So you wouldn't develop that kind of application for one go visualization. The idea really is to try to do something that you can share with people and that you want to use and reuse multiple times. And so a Shiny application is built around two parts.
Yeah.
So a Shiny application is built around two parts. One is the user interface. It's the kind of the front end that the user will interact with through the browser. And the second part is the server side. And so the user interface will be defined. So let's see. Let's say here we have a user interface. And the user interface will define well exactly what it says. The user interface. So if we want to have a title, that would be defined. So in the user interface, we might want to have, and we will have, a sidebar panel, a main panel like this. All this is encoded in the user interface. And the second part would be the server side. And that's the part that will kind of get information from the user interface, specific inputs. Let's say here we have a certain input, and that input will be passed to the server. And the server will do some calculations, will interact with the R engine, do some calculations, produce some plots. And these plots will then be kind of sent back to the user interface as outputs. So when we will write this code, we will see input variable and output variables, and these are visible both at the defined at the user interface level, and then passed, processed at the server, and then sent back to the user interface. And now, another concept that is specific to developing Shiny is called reactive programming. And so we will define some functions here on the server side, and these are reactive functions. So they kind of don't do anything until the user modifies something in the user interface, modifies some input, and that will trigger these functions on the server side that will automatically be run, update or calculate some output, will be then sent back and re-rendered at the user interface level. So to develop this application, what we're going to do is that we're going to create a new directory in which we're going to put this application. So I'm going, for example, to call it my app, and I'm going to put this directory in my project. And in this directory, I'm going to create two files. Let's create these two files. I don't see any new file button here, so let's create a new script. And I'm going to store this script inside my app. And one I will call UI.R, that will contain the code for the user interface. And then I'm going to create a new script that I'm going to store in that application folder, and this one I will call server.r. So I have these two files here inside my directory. Now, here to kind of highlight the fact that I have two files or two parts, I'll create these into two different files. These two parts of my Shiny applications, the user interface and the server, could also be written in the same file, and we'll see a little bit later how to do that. And the data that we are going to use is the faithful data set that ships with R. That is, these are information about the eruptions of volcanoes in the Yellowstone National Park. And here we have the duration of these eruptions and the waiting time between two eruptions. And so what we will visualize, the data that we're going to use here, faithful, we're going to look at the waiting time between two eruptions, and now we're going to visualize these using a histogram. Okay, so it's essentially these visualizations that we would like to render the Shiny application, but including some user interaction. So let's start with the user interface, and we're going to build this application step by step. So here I'm in my UI.R file, and I'm going to start developing my user interface. So the first thing I need is to load the package Shiny. And the way I define a user interface is with the Shiny UI function. So this file will contain the call to the Shiny UI function. And as part of the UI, what we want to do is to define a page. And here is the fluid page. Okay, so the fluid page is the type of the user interface will be based on that type of HTML page. Okay, so that's the kind of high-level container. That is the full page. And inside this page, we will add a title panel where we can define the title of our page. For example, here my Shiny now. We will also want to add a sidebar layout. So, and inside that sidebar layout, we will have a sidebar panel, and we will add some code, some inputs to the sidebar panel inside here. And in addition to the sidebar panel, we'll want to add a main panel here. So what we have done here is essentially to define a page with a title, a sidebar panel, and a main panel. And the little red marks indicated that I forgot some comments here. Okay, so let's go now to the server.r file. We will also need a call to library Shiny. And just as the UI contains one call to Shiny UI, the server will contain one call to the function called Shiny server. That's all we build. That's the only call, or the main call to a function in the server. And here we need to define a function that will take some inputs. That's what the user will provide in the user interface, and some outputs that the server will calculate and then return back to the user interface. So we have to find a kind of infrastructure for the server, but the server doesn't do anything so far. And we can already run this app by simply providing the directory in which this UI and server files are defined. So, did I start Shiny? My app. And so I run my application here with the run app function. I provide the name of my directory, some sidebar layout, some typos. site. And here it is. So I have a title, my Shiny app, my in gray here, my side panel, and my main panel here. So here I have created my first Shiny app. That doesn't do very much. It just displays the user interface. So what we're going to do is to add elements to this different user interface and then process them in the server and slowly build up an application. So would you like some time to finish these UI and server applications? Or did you have enough time to do that while I did it? So would you like some time, or shall I just carry on? I see everybody nodding, but I'm not sure. And I see green sticky notes for that. So let's say green sticky note if you're happy to carry on. Otherwise, I'll give you a little bit of time. And by the way, you don't need to copy everything. All these code chunks are available kind of level by level in the lecture notes. So this is the first iteration of the user interface, and this is the first iteration of the server.r. So if you would like a little bit of time, I can give you a bit of time now. Otherwise, please use your green sticky notes, and I will pass the new ones around. If you want me to continue. Okay. So what we're going to do now is to add some inputs and outputs to user interface, and then process them and update them on the server side. So let's start by updating the user interface, and what I'm going to do in my sidebar layout, I'm going to add a text input, a call to the text input function. So that's a specific special type of function that will get some input from the server, and the type of input that we have is some text. And we're going to call it text input simply. So that will be the name text input of the variable that we will use to communicate between the user interface and the between the UI and the server, and some default values here. Sorry, some string that indicates to the user to enter some text here. That we are adding to the sidebar layout here. So let's also add something in the main panel. And here we are going to put a call to text output. And this variable we are going to call text output. So here, text output, text input, this is the name of variables, and we could choose whatever we want. But here, text input here and text output here, this is the name of these reactive functions that are defined in Shiny. So let's update the server part now. And so the server is a big function. We see here the call to function. And we have inputs and outputs. So if we say output $text, so here, text output. So that means that we're going to pass an output back to the, and which variable do we want to update, to change, is text output, the one that was created before. So we want to assign it, what we want to do with it. So we want to do some rendering. We want to create some data and render it by passing it as an output. So what we want to render here is some text, so we use the render text function. User entered text. And here we are going to take the input, and the input was called text in. And the way we want to create this text is by pasting. Paste is a plain R function, and we want to paste this text and add to this text the content of text input, okay, that we can grab from the input that is passed from the user interface. So let's come back here and rerun our application, our updated application. And I have a label that is missing. Let's see. User interface. Sorry, this is not a column. Here we go. So we have added, back to the our app, we have added in our side panel text input that as a user I can now update. And this is now the text input that is passed to the server, and the server creates this new string by pasting user into the input and whatever is stored inside here, and then combines these, sends them back as an output to the user interface that now displays it in the main panel here. Some additional outputs to our interface. And this time we don't want to add a text output, but let's produce a plot output. With the plot output function. And here the kind of identifier, the variable that we want to use to refer to this plot is this plot. This plot, because if we look at we will want to look at the distribution, okay, of this, the weighted times. So this plot we're going to call this plot, and it's going to be rendered with plot output inside the main panel of our user interface. The that we do to user interface here is to add a specific output, and now we need to create this output, and this is done on the server side here. So we want to calculate, create a new output, and the specific output that we want to create or update is the dist plot that we generated before. So the plot needs to be rendered with a function called renderPlot. And inside here we are going to write the code. And given the fact that the code will span multiple lines, we need to write these multiple lines within curly brackets. So everything that we're going to write inside here is code that will produce a figure that will then be rendered and passed to as output to the variable distplot that will then be rendered in the user interface. Let's create a variable x that contains the actual data that we want to generate, and here is the data that we will want to produce a histogram of x. So here's how we are going to create the disk output, sorry, the disk plot figure that's going to be rendered in our user interface. So let's rerun the application. And here it is. So this is the kind of materialization of the plot that we have that is produced on the server side. So currently the only thing that we have is to visualize a static figure pretty much the same way as we would have in R, and we'll now add some interactivity to this plot. Yes, sorry, I see you. Okay, currently the only interactivity that we have here is through this text box. So let's come back to the user interface, and what we would like to add is in the user interface here, add a new widget, a new component in the sidebar panel. And what we want to add is a slider input. Must not forget my comma here. A slider input so that we can parameterize the number of pins that we see here. And this will be controlled by a slider input that the user can move towards the right or the left if they want to see more or less pins. So the first thing is we need to provide a name to this kind of new variable that will be created in the user interface and manipulated in the server, and let's call this one pins. Pins will be the name of the thing that is passed through the inputs and outputs. Some descriptive text that will be displayed in the user interface, and some values, and specific values that we have for this type of widgets is a minimum, a maximum, equals 50. So here we will want the minimum value and the maximum to be from 1 to 50, and the default value to be 30. We can actually run the application here. So what we have defined is the following widget in the user interface. It doesn't do anything for the moment. Slider input from 1 to 50 with default value 30. But now we also have a variable called pins, and that's how we have defined it here, that we can use on the server side. So let's now update our server side to use these pins. And we will want to use this to update our plot and specify the number of breaks that we want. So this is an object, an input or a parameter to the hist function. And so this value pins we want to calculate using the sequence, the set function, in the following way. We want these breaks to go from the minimum value of x being a variable that contains these data, from the minimum to the maximum, and then we'll define how many, I will define these breaks by setting the intermediate ticks. And here this we can do with the length dot out equals input dollar bins plus 1, where input dollar bins is now the user set value through the user interface. So let's restart our application. Okay, here. Pardon?
So from minimum to maximum.
Oh yes, thank you. And so now the default number of bins is from the minimum to the maximum with 30 bins. And this is something that, as a user, I can now change. And I still have here my text input that I can use. Let's keep on adding ways that as a user we can parameterize the figure. Still in our sidebar panel, another type of input, for example, the select input. That is a kind of drop-down menu so that the user can choose a certain set of values.
So what was the reason for +1 in the Dropdown?
That's to define, that has nothing to do with shiny. That's the number of bits that we want.
So what was the reason for +1? Why wouldn't we choose
So let's see, x faithful 2, is x, here's the figure, and so bins sec from min x to max x length dot out, let's say 30. What do we so these are these bins. If we say +1, we get one more, and what do we get here? Yeah, to be honest, I'm not sure. It would probably maybe work without it once. We can try. I'm sticking to my script. Otherwise, it might get a bit difficult, but let's save it here. I'm going to remove this for a second. And rerun it. Yeah, I don't think there is a specific reason. Yeah, I don't know why there is a +1. I don't know why it comes. Apparently it works without. Maybe it works without. I don't remember why it specifically went for +1. But that's nothing that has strictly to do with shine.
I was just curious.
Yeah, no, good question. Fair enough. You should always question what I do, not take it for granted. Right. So let me come back here. My control set. Yeah. So let's now select input. So add a new widget to the interface. And what we want there is the user to be able to select some values from a drop-down menu. So as always, we start by defining the name of this variable that we pass from the user interface to the server. So we had something that we call text input bins, and here we're going to call it col because we would like the user to change the color of the histogram. Some text that we're going to decorate the user input, select the color, and then a set of choices. I must not forget to come up here. A set of choices as a character vector, and for example, I'll give the user the possibility to choose between dark gray and orange. Matter here. Here we go. So input $col, input output $col is something that will contain now the color here, and we want to make use of this in the user interface, and we can use it immediately. Input $col is the selection of the user, and we want this to set the col parameter to our hist function. And here we can rerun the app. Here's the new select input, the 3 choices that we defined, And whenever one choice is defined, it's passed through input $call to the server side and used to fill out the bits in our histogram. And so the last update that I propose here as part of this app development is in our user interface. Let's add at the bottom, under the histogram here, a list of all the data. Okay, so let me rerun the application here. And so let's add here under our graph a table, a little bit like the one that I showed for the GUI application. And so there is a new type of outputs on our text output and pop output, which is the data table output. And let's call this, again, we need to provide a name for that variable, data table. And these different outputs here, we add them under the main panel, and the different inputs under the sidebar panel. So now we need in the server to define, initialize, and update this variable. So let's move back to the server. Here we go. So output $data table. And here we want to do some rendering, and the rendering that we want to do is the type of rendering. It's for a table, and the data is readily available, and that's the faithful data set or data frame that we also reuse, that we also have here. There we go, and let's start the application again. And it doesn't show up. What am I missing? Let's see. Oh, render data table. There we go. Yes. And so this is kind of HTML presentation of this faithful data frame. And the features like the one I showed where I can search is, for example, readily available. If I search for 54, it will select or filter all the rows that have a 54. And I can also here sort my values. And again, this is something that comes out of the box with the data table rendering. So here we are, two components, the user interface.r and the server.r, that here we implemented in two files inside the directory. But these two could also be all the code here, the Shiny server code, and the Shiny UI, or the call to the Shiny UI function that defines the user interface. These two could also be defined into a single into a single file here, where the fluid page is assigned to a variable UI. The function for the server is assigned to a variable server, and then we can start this with Shiny app UI equals the fluid page server equals this new function that we define that acts on the inputs and updates the new outputs. So two ways to do the same thing. Yes?
So for the function render table, it looks like since you did not do anything else rather than using the function render table, which means that the options of sorting the values and the search options, they were inherent to the function render table.
Yes. And so actually you can also do this table rendering independently of Shiny by loading a package called DT. That is not installed, but let's do this quickly. DT. yes, DD for data table, and it's a JavaScript library that has this kind of R package interface. Right, so if I load package DT, and so let's see what do I have in here. Well, CRCDF, here's this data frame, and I can use the function now, data table from my DD package. So table components directly here inside R. And all the functionality can be customized, and all this is described in the library, but all the functionality comes out of the box. And so, for example, if view is not enough, we have used view many times to kind of look at the data set. But if that's not enough, if you want to be able to sort or so additional interactivity, DT, data table, is something that can be used interactively, or used as specific components of your Shiny applications. So there are many different ways to share these Shiny apps that you have developed. So you can post them online on Shiny apps. Dot here. So on ShinyApps.io, you can create an account, and then everything that you develop locally, push them to your own account on ShinyApps.io. And the example that I showed you before is exactly that. Under my account, I have an application called Christopher 2015. It corresponds to the 2015 or 2016 paper, and that serves that application online. There are, of course, some limitations if you want to use the free account. I think there is a limited number of apps that you can have. I think it's 5, and it's kind of the least powerful backend, but you can pay a couple of $100 a year to have tens or so applications, or even more if you need private or log in through specific accounts and so on.
So what's the benefits of uploading scripts to Shiny online?
Well, so for example, as part of this draft map of the mouse, blah blah blah, understands that spatial proteomics or spatial proteome, as with the publication, we released some software. Or there is some software, we released the data, and also we released the Shiny app. So if you want to visualize these data, you can download the data, install Prolog GUI and look at it manually, or somebody else that does not have R can simply go on that interface and visualize the data without having R or Shiny installed.
So that can also be done just by sharing the HTML link?
Yes, exactly.
So what's the benefit of the platform of online Shiny? Why should I create an account or for example, for GitHub, we know that what's the benefits of creating an account?
Oh, so you can access this without account. If I want to have this created Shiny app, I need an account.
Yeah, so for example, for Shiny app, you just need your RStudio and R, right? You create everything and you created your Shiny app, and you have you can share that Shiny app through an HTML link, if I'm not mistaken. Is it correct?
Okay, so there are multiple ways of sharing your application. Your application needs to be somewhere online. Okay, so just give me a second, and I think this will answer your question. There is another way where I can share or rerun this application. It's with the following link. So in R, I can type run GitHub, and then say inside this GitHub repository, under this person's name, specifically inside this subdirectory, there is a Shiny app that I can run. So I'm going to go back into my R. and type exactly this. Okay? And so what R and Shiny in particular is going to do, it's going to download this repository. You can see here, downloading, extract it, and start it. So the application that we wrote, everybody can now run it, but that means that they need to have R and the Shiny server, okay? Which is fine for many people, but some people will refuse to use R, and they will demand to be able to access the data on their phone, for example, or and so then you would need to kind of externalize this functionality. And that's when you might want to use shinyapps.io. Or there is another possibility, and that would be to install a Shiny server in-house. So one of your kind of public-facing servers, you can install the Shiny server, and then that server hosts your applications. And so the URL would not be something like your username at shinyapps.io / the name of your application, but it would be yourserver.org / the name of your application.
So for that also the viewer need to install that in-house thing?
They won't need, because the server will run Shiny. So it's the equivalent of Shiny apps, but instead of being on our studio's Shiny apps cloud infrastructure, it would be on your server. Then you would only need to share that URL, and people would not need to have R installed. R would be running, instead of on the cloud, our studio's cloud infrastructure, it would run on your private server.
So for that in-house server, do I need to pay for that, or it's free?
No, you can download. So I'm not sure if you get all the function. If you don't get the same functionality as in Shiny.io. Yeah, I don't know my account by heart, so I can't log in. But you would kind of install it locally, and you would provide apps with the URL to your server. And that's a package, I think it's called Shiny Server, that you install on your server that runs R and runs Shiny. So if you have many applications and you don't want to pay for shinyapps.io, and you have the in-house skills to set up the server and run Shiny Server, which is not particularly difficult, but it requires some maintenance, you could do that. So certainly for a group that generates many applications, that's probably the easiest thing to do.
So in terms of publication requirements, do they have any difference over one over the other in terms of the journal publications?
Journals don't have any expectations. That's something that we wanted to do because it's an efficient way to share our data. In addition to sharing the actual data, sharing an interface to the data. And it actually proves super useful, to just display an application without having to run it. Yeah. And so run app for locally. If there is a URL, it's possible to run it from a GitHub repository or from a GitHub gist immediately. Shiny apps, Shiny. And so there is much more interactivity that you can set up than what we have seen here, that you can set up from Shiny apps. Or you can, of course, also display ggplot2 types, and it's not really, limited to base plotting. But as I discussed yesterday, ggplot2 figures, actually producing figures in ggplot2 is much slower than in base plotting. So we don't realize it when we do only a single figure. Actually, we do realize it on this computer. But in general, interactive, you don't realize. But if you need to update big figures or generate many figures, this is certainly something that can become slow online. My experience also with Shiny apps is that when you start to link different plots, tables, and things like that, this also tends to slow the user experience quite a bit. So Shiny is certainly really nice as R programmers, but there is no way it can replace custom JavaScript like the things that we have seen earlier this morning. But of course, it requires to know JavaScript. Okay, and tons of references, like most of the products that are released by our studio that comes with quite a bit of user documentation, which makes it useful. Okay, so that's all that I had to share with you for this afternoon, and I'm pretty much on time. So are there any additional questions either about Shiny Plotly or more generally about, oh, there is one thing I wanted to mention. So I talked about Bioconductor very briefly and mentioned this kind of a project of R packages dedicated to the analysis of biology. And you can follow this link here and kind of browse and search all the software that is available within Bioconductor. And each Bioconductor software is tagged with what BioCU labels that will tell you whether this piece of software is dedicated to, for example, cancer, or provides data about human, or is a software for proteomics, transcriptomics, and so on. And among all these tags, there is one called visualization here. And so in Bioconductor, there are 437 packages that have this tag visualization. So for example, if you want to plot networks, there is a piece of software called GraphViz that allows you to plot networks. And there is an R interface, so all GraphViz could be used to kind of render these graphs from R. And so here we are, tons of packages that are dedicated to visualization, either specifically, so like RGraphviz is something that is kind of low level for visualizations, but kind of cluster profile, which is a package for gene enrichment type of analysis, and that supports the visualizations of these results. So visualization, BioCView will list a set of packages that somehow deal, maybe not exclusively, with visualizations of these high-throughput biology data. Voilà, thank you very much. So please don't forget to fill out the feedback form. Yes?
Was the rank number, has that
Pardon?
the rank number, does that have
Rank.
rank?
On the right-hand side,
The software.
the right column.
Oh, rank. Oh, I have no idea. That's a new thing.
Based on number of downloads, I think.
Yes, probably. So our track layer is the 19th in the. So if you look at each package, you have where is it? Download stats here. And so if you go back here, all the packages are listed here with the number of downloads. Oh, here we go. Rank. I don't know. Maybe it was 37, but that's probably what the rank means based on. So if your criteria to choose a package is based on how many times, I don't know, 19, so maybe that's 19 within the visualization, I don't know. But I assume it's based on the number of downloads. All right. Well, oh, yes?
I'm not sure if you have time for this, but could you maybe give some hints on how to debug Shiny apps?
Oh, that's a very good question, and that's actually very difficult to do.
We actually had a speaker in advance, one of our keynote speakers in advanced R talked a little about that. Barrett Schlarke, they have a new R package called React Log that will help you debug a Shiny app. You start your Shiny app and then so it has to at least run, but it can have some stuff wrong with it. And it'll show you a graph, essentially, of the different inputs and outputs and the reactivity that's going on. And so you can see if a certain input is not setting a value and you think it should do something, but it's not, it'll help show you that.
But that requires a specific package.
What was the name of that? React Log?
Can you go stepwise there, or can you go into functions with that thing?
So if you wanted to debug inside functions, then you would probably need R's existing built-in debugging tools, like say in a browser or using the debug function. The React Log is specifically more for the understanding how Shiny is reading the different inputs and how those are updating reactive values and things like that. So the stuff that you can't debug with R's traditional debugging tools.
But that's certainly something very challenging, debugging. I've never used React Log. I think it came out very recently, but that's very challenging. Something else that your Shiny apps can have return values. And I think that's so you could create a, so here when we run here result, so you could have at the end of your Shiny app a return value that you could reuse in R, which is something that I sometimes reusable. If you want a little Shiny app to do some selections in kind of big objects, you can encode it as a Shiny app and then return them back into R. One slightly, I think, annoying thing, but that might have been allocated recently, is that when you run an application, a Shiny application, and maybe that's by design, your R console is blocked. So you cannot keep on using R while the Shiny application runs. So you could run this in the background in a new R session. But yes, it would require a different type of infrastructure if you wanted to manipulate the same data from R and from your Shiny app. This is possible, but it requires different types of packages. Okay, voilà. Thank you very much.